Right, I'll start anyway because we've only got 10 minutes. I mean, this is like preaching to the choir here. Shall I explain what memory corruption is?
Yeah, if you start announcing it, maybe people will.
Yeah, okay. Okay, so obviously when we're looking at memory corruption and buffer overflows in particular, so typical cases where you have a buffer defined, and because CPUs, yeah, say good. Because CPUs typically use integer values to reference memory, then that integer value is unconstrained. So if you have a buffer, by modifying the integer value, then you can read off the end of the buffer and access something that you shouldn't. So either read or write. And this is typically either as a security exploit or just as a bug in the software. And this is just memory corruption. So to address these type of problems, there's a security technology called CHERI, which is Capability Hardware Enhanced RISC Instructions. And CHERI is a memory access protection technology. And at the basic level, what it does is replaces the integer pointer use within the CPU with effectively a new hardware type, which is a constrained pointer or a capability. So a capability includes the integer part of a memory address, but it also contains some metadata with it and some writes. So that includes the bounds of where that memory address can access and permissions as well. So for instance, read, write, execute. So you can see that here. So this is the typical format of a 64-bit capability. So we have our traditional integer address down at the bottom, and then we have a bounds which constrains that to within a region, a buffer, and a set of permissions. As I say, can be read, write, execute, but there are other ones as well. So you can think of a capability as well as a token that represents memory access, as opposed to just an integer value. And what we do in the system is pass these tokens around. We can derive other capabilities from a capability, but it must have less writes every time. So either the same or less bounds, or the same or less permissions. And that way we can start at the start on boot with a capability that covers everything, so all bounds in memory, all permissions. And then as we go along, we constrain it to smaller and smaller things. And a lot of this is handled in the compiler. So for instance, if you define an array, then it will create a capability that has the address of the array, but also just the bounds of that array. So you cannot write beyond it. So at the moment, we're working within RISC-V International to turn this into a standard extension. So it's an open specification at the moment. You can just go and download it from GitHub and get involved there. And we have, for this demo, implemented it on an FPGA. So what we're going to show here is, hopefully, Linux booting. So what we've done in this case is we have replaced all use of integer memory addresses in everything from secure boot, OpenSPI, U-boot, and the kernel, and user space applications as well, with the capability versions of them. So we call this pure cap for pure capability. So in this case, the kernel and everything as part of the boot stack is all spatially memory protected. So in terms of the boot chain, you'll have secure boot, which is Codasip's own code, and then all the rest is standard open source softwares that have either been modified slightly for CHERI or just a recompile, as is typically the case with user space applications. We have to modify some of the lower level code that handles memory. So if you think about it now, you have additional things you have to worry about in terms of things like memcopy or string functions, because you have to preserve the capability tags, which is an additional hardware controlled bit for each capability that says whether it's valid or not valid. So it's a way of maintaining the integrity. Okay, so we will hopefully try and boot the board. Yeah, get it. So this is just a serial terminal. Connect to the console for. So at the moment, it takes a minute to load the bit stream, but after that, then it should hopefully load the software. So there we go. Bit stream's loaded. So now we've seen it going into the Codasip loader. So that's pulling in U-boot at the moment. We have to give it a minute because this is running on an FPGA. So this is the Codasip X730 CPU. So it's an application core, dual issue, running at 100 megahertz on the FPGA. Okay, so now we've gone through U-boot and we're now in the Linux kernel. And as I say, this is running with full CHERI protection on here. There is no integer access anymore. It's all capability protected. And so far, we're now at the stage, so this is quite an early stage of the Linux kernel development with CHERI. And we're working also on expanding the set of user space applications as well. So this is running a BusyBox system, so relatively simple, but we've already started pulling more complex bits of software, like web servers, things like Exum, mail server, and other standard Linux stuff, really. A lot of it doesn't require much modification, if any. Once you get to the application level and all of things like memory allocators are abstracted, then typically it's a recompile. It's only if it's doing some particularly low-level stuff like JIT engines or something like that, then that requires support in CHERI. So at this point, we should be able to log in. And it just behaves exactly like a normal Linux system. But in this case, it's completely CHERI protected. So, okay, I think we have maybe time for a very quick demo with. Let's see if we can bring up both of them. So what I'm going to show here is if it comes up. There we go. Okay, knock that out. So we have here two systems on FPGAs. One of them is a standard RISC-V, no CHERI, which is our A730. The other one is our X730, which is the same CPU, but with CHERI configured in. So again, ordinary Linux system. So what I'm going to show here is an old vulnerability in sudo, or sudo. So I can see on the standard one, I can do who am I, user demo. I can then run the exploit for sudo. And if I do, you'll see I've now done a privilege escalation due to a vulnerability from being the demo user up to being root user without having to enter the root password. If I try the same thing on a CHERI system, okay. In that case, you can see the exploit has failed. Started off as demo user, still the demo user. And if I switch back to the console, you will see in the console logs that we have a CHERI exception has been caught. It's not clear to read here, but this says CHERI data failed to load, cause length violation. So it's essentially picked up the buffer overflow that was the cause of that vulnerability and has just stopped it dead, killed the process. So, okay, that's just a very simple demo of Linux booting and CHERI protection in action. So, thank you.